That's why I wanted to make sure there was a mic there. But all right, so I'm going to do my best until they get that working. And okay, so yes, I'm Fernanda Foertter, and I just recently joined NVIDIA about 4 months ago. And my role there is one of developer relations. They originally called it Alliance Manager, and I thought that doesn't mean anything, so I'm going to give myself a new title. My boss went with it, so I'm calling myself a GPU developer advocate. So that's basically what I do. I try to find people that are developing on GPUs and make sure that they have everything they need and they have a good time. Peter Mesmer was the one that I blamed for this talk. He's the one that threw this on me and didn't give me any slides, so his name is Mud. Just if you see him, his name is Mud. Yeah, so neural networks, complexity is getting even worse. For example, the 100 exaflop example here on the Google side, it's estimated that would take like 2 years to complete in some sort of infinite infrastructure that Google might have or may not have, right? We don't know the exact numbers, but that's not very doable. But we'll do the best we can in terms of creating hardware that can do this sort of work. So as a GPU developer advocate, the biggest thing for me is to understand your needs so that I can develop this into a software stack. Running on hardware without software is useless, right? Software means everything. So right now, our goal is really to make sure that the software stack is there and available. And to that end, we are accelerating all of the major frameworks, and we support all of the above. And it's an extremely daunting task because they're popping up all over the place. And then some of them may be more supported than others. And so understanding, for example, where the community is and how much of the community is using a particular framework is something that we can help prioritize. So that's my job, is to kind of go over there and say, hi, my name is Fernanda. What framework are you using? What application are you using? So we can help prioritize these needs. So that's the layer you guys see. And then there are all the other layers on top of that. So on top of each of our pieces of hardware, we have an architecture-specific optimization layer. Right? There are basic math operations that happen within these frameworks. And these primitives, we call them primitive libraries. And that's where we really spend time optimizing specific to our hardware. And that is things you probably know. And if you've tried to build TensorFlow, for example, trying to build it with cuDNN, you try to build it sometimes with other communication libraries, and cuBLAS, cuSPART, all those things are the sort of basic building blocks of each of these frameworks. And so we spend a lot of time, but lately what we spend a lot of time on is the multi-GPU. The DGX has 8 GPUs, and DGX2 now has 16 GPUs, and that's where we spend a bulk of our time trying to optimize those layers. And then, the network description, end of it, workflow, hyperparameter sweep, those are still very much a moving target, especially the hyperparameter. It seems that everybody's really interested in hyperparameter searches. And so if you have a hyperparameter search out there, you would be very popular to put it in GitHub, because that's what everybody wants. Mostly people that are getting started on deep learning are doing it by hand. How many of you are doing it by hand? There you go, right? So if you've built one, these people would love to see it. And also we'd love to talk to you about it. The data and job management is still difficult, especially as we're combining HPC plus AI. And running some of these frameworks on HPC infrastructure, which is not normally built for that, can be a little cumbersome, but we're really working on making this usability much nicer, especially with containers and the K word that I can't remember right now. So productivity layer is really important to us. If you have productivity issues and you'd like to learn more, talk to us. All right, multi-GPU deep learning training. So let's talk about that. So the figures I have here, unfortunately, I didn't find figures for DGX2 quite yet, but the figures I have here on cuDNN go all the way to DGX1. And we've spent, to see how much has progressed. Sorry, Siri wants to talk to me right now. To see how much has progressed over the years, this is really how much we put our focus on optimizing and updating. It's very easy. You can use it as a drop-in library, right, to at least just all of the major frameworks, and it's especially tuned for our hardware. And the other thing that we've really been working on is this thing called Nickel. How many of you are running your frameworks on GPUs right now, and do you build it against Nickel? Okay. So Nickel 1 was actually a closed source before, and there is, open source before, and then there's some talk about closed sourcing Nickel 2, and then finally they open sourced it. So, so I'll tell you in terms of NVIDIA, what I've learned in the last 4 months. The developers and the dev techs within NVIDIA love open source, and then sometimes legal gets in the way. And so if you see something that's closed source, it's probably an infighting going on, making sure that things get open source. So we're on your side on that one. But Nickel works on both PCIe and also our new switch topology. And it can also go across nodes. So it also works over IB verbs. And that's really, really important if you're trying to scale training. Yeah, so I'm going to use some examples right now that involve DGX1 because I just don't have the pictures for DGX2, but they apply to DGX2, they apply to actually architectures that are based on PCIe. DGX2 has NVLINK 2 connected all around with the GPUs, and so this applies the same way, really. So how we can do data parallelism. So we can do two things. We can do how we can scale in deep learning. We can do two things, either model parallelism or data parallelism. Where GPUs really come, at least NVLINK and also Nickel really come in handy is spreading the data around across GPUs. That makes the effort on trying to figure out data parallelism much, much lower. So here's one thing that you might see. This is a typical architecture. You have CPUs connected, for example, in this case is an Intel CPU, right? It's connected over QPI. And then you have a PCI switch that connects over 4 GPUs. And so you can load the data to these GPUs over the PCI switch. And you can also sort of slosh data around between CPUs over QPI, right? And for example, that would be interesting for sharing the gradient or updating gradients. So there's some congestion that happens as you're trying to communicate gradients, right? That one QPI is one of the slow points, and also you have to share this PCI bandwidth across all 4 GPUs. So what's really handy about NVLINK is that it skips it all together. And so we've built something very specific for scaling because now we can do the data loading over PCI, but the gradient averaging, just the GPUs communicate with each other. So you really don't have to think about it, and that's what we're trying to do is just make it so that your lives are easier. And now there's no congestion, even though he colored it red. I don't know why they colored it red. They should have colored off kind of gradients in green. So DGX2 is the next generation of that, and it's a behemoth. I don't know if you got to see it if you were at either supercomputing or GTC or ISC. We have a DGX2 that's available, and you can go in there and see it and touch it, and don't touch it, actually. They get very upset if you touch it. But what's really interesting about this is that it has NVLink 2, which has upwards of about 900 gigabytes a second of bandwidth, and that's out of this world insane, right? And 16 GPUs, and also has this really cool thing in the back end called NVLink, which NV switch, which I'll talk about next. So we decided to go and build our own switch. Why would we do that? Because we can then control a lot of the hardware and make that that single machine with 16 GPUs just seem like one giant massive GPU to the framework you're using. And that makes it very easy for you guys to do data management and model management and running. So 16 tells us GPUs. We heard you need more memory on your GPUs, so we upped the voltus from 16 gigabytes to 32 gigabytes. You get about 2 petaflops worth of deep learning compute, so that's including the tensor cores that you've heard about at half precision. Have a whole half a terabyte of unified high bandwidth memory, and you have 300 gigabytes per second from GPU to GPU, and a total of 2.4 terabytes per second total cross-section bandwidth. So again, your framework would just see a single GPU, and that's really, really easy. You get about 2x performance compared to DGX1 using NVSwitch or another sort of flavor of that you might have that has NVLINK between the GPUs, so maybe a Dell or some other partner that will have NVLINK. And of course, you can decrease your training from 15 days to 1.5 days, so that's your time. We value your time, and this is important. As far as the frameworks, you might be wondering what frameworks will work best, which ones are you optimizing? It really doesn't matter. For the most part, they all perform really well, and all the way up to 8 GPUs. So the major takeaways is, so here's some considerations that we've learned in the last 2 years on how to do this best. So the first thing is pre-process your data outside the main training loop. That's very important. Get your data ready for compute. And that's actually the bottleneck that I see for most people. So my area right now is healthcare, and I'll go into areas, like go into hospitals and say, hey, what are you guys doing? Oh, we really want to do deep learning. Great. You have data. Yes, we have tons of data. We got electronic hospital records. We got all sorts of images. Great. Where are they sitting? They're like, well, the images are sitting over there, and our health records are sitting over there. Like the data is not ready for compute. And that's really important to facilitate model training, especially as you go over iterations or you're doing hyperparameter sweeps, right? You can use high-level support for data loading on the GPUs if you have that available. But beware of CPU bottlenecks, especially as you're loading data on systems that don't have that nice NVSwitch or NVLINK 2. There are specific builds. I have actually some extra slides that I'll include as part of this presentation as sort of backup slides, and there are specific flags and that you can do on all of the frameworks. We have about 7 or 8 frameworks that we've included in slides. They have flags that make sure that they're optimized for multi-GPU. Let's see. And what we found, like I showed you before in the graph, is that all deep learning frameworks can achieve good, just about equal multi-GPU support. A part of that is because of the primitive libraries that we built on top of our hardware. How you engineer the model training, though, can differ significantly, and so that can affect a bit your performance as far as speeding up the training, not performance of actual training. The monolithic frameworks offer less opportunity to shoot oneself in the foot. So if you're going to production, use the monolithic ones, use the ones that have been around for a while. If you're brave and you're feeling extra energetic, you can use one of the new ones like Paddle, which is coming out. They all offer obviously high-level interfaces, but where you really get performance is really by either compiling with low primitives or compiling over IB switch or IB networks. And that's something that we'd love to hear from you if you're having trouble with it, if you'd like to understand how to do it, if you're just not getting into work. I know I used to work at Oak Ridge National Lab, and one of my jobs one time was to build TensorFlow with MPI, and that wasn't fun. There were days of my lives that I lost that I just can't never get back. So multi-GPU trainings, here's the conclusion. Multi-GPU training is critical to effectively handle many important problems. The correct choice of hardware, obviously we'd like for you to use our hardware. We think that's the correct choice. Other people might have other opinions, but it's my talk, so. And for many problems, linear scaling is actually really possible, and we've seen that at Oak Ridge. There are groups right now at Oak Ridge running on Summit that can linearly scale to hundreds of nodes, and we've seen that be very, very useful. And if you're doing model scaling or independent scaling over your particular data sets or particular slices of data, that, basically linear. All right, and I've reached the end of my backup slides.